Hi, my name is Shahnaz. In last lecture, we introduced the concept of primary decomposition, and we did the following theorem. So this theorem states that this theorem has two items. Item first is that every finite abelian group G is direct sum of its p primary components, and the second item is if two finite abelian groups say G and G prime are isomorphic, so they are isomorphic if and only if their p primary components are isomorphic for each prime. So first item is every finite abelian group say G is the direct sum of it is p primary components. That is G is the direct sum of GP1, GP2, so on GPN, while these PI's they are distinct primes. And the item second is that two finite abelian groups say G and G prime, two finite abelian groups say G and G prime are isomorphic if and only if their p primary components are isomorphic. That is GP is isomorphic to G prime P for every prime P. So this item first, this has been proved in previous lecture. Now it remains to prove the item second. So this is the item second, proof of item second. So we first assume that these two groups G and G prime are isomorphic, then we'll prove their p primary components and isomorphic. Then we'll assume this holds and we prove these two groups are isomorphic. So let us assume that these G and G prime are isomorphic, and let us consider a homomorphism between these two groups. So let f from G to G prime be a homomorphism. And let us take an element say G in p primary component of G. So this is in the p primary component of G. So if G sits here, then p to the power some integer say L of G, this is 0 for some integer say L which is bigger or equal to 1. Now f being a homomorphism, it takes 0 to the 0 of G prime. Now so this 0 is same as f of 0, and f of 0 is same as f of PLG, because PLG is 0. Now this is p to the power l of f of g, because this plg is nothing but so f of plg. So this is sum of these g's, so they are pl times. Now f being homomorphism, this means that this is same as fg plus fg plus fg so on plus f of g. Now these f of g's are thereof they are pl times, so this, that is why this pl came out of here. Now f of g being an element of g prime, so this pl f of g equal to 0 implies that this f of g is in g prime p. This implies that this f of g, this is in the p primary component of g prime. Now we took an element g in gp, and we showed its image is in the p primary component of g prime. That means the image of gp under f is contained in g prime. This shows that this image of gp, this is contained in g prime p. Now it is given that g and g prime are isomorphic, and let f be such isomorphism. So let us assume so let f be an isomorphism. That means f is bijective as well. So if it is so, then its inverse is isomorphism as well. Then f inverse, which is a map from g prime to g, is also an isomorphism. Now if f inverse is an isomorphism, then by the same argument over here we have f inverse of p primary component of g prime is contained in p primary component of g. So it follows that each restriction that is the restriction of f on the p primary component. So this is a map from gp to gp prime is isomorphism. So similarly, it is inverse on gp prime is also an isomorphism. So this follows that so therefore now if this is an isomorphism, it means that these two groups here, gp is isomorphic to gp prime. Now let us prove its converse. So conversely, let gp is isomorphic to gp prime for all p, for every prime p. Now what we had to prove, we had to prove these groups are isomorphic as well. So now it is given that these two groups are isomorphic. Let us consider an isomorphism, say f of p between them. So let f sub p from gp to gp prime be such isomorphism. Now define say a map, say this phi from direct summation of these gp's to direct summation of these g prime p's. So this map is defined as it takes an element here which is like this to this map takes this element here. So let us try this in this way. So an element here is of the form gp1 plus so on plus gpn if this sum is from 1 to n. So this phi takes an element here which is of the form sum of these gpi's. So it takes this element to sum of now from each gp to gp prime we have a map f of p. So it is sum of these f p of these gp's. Now let us take p here. So it takes to this gp. So one can note that this is a homomorphism. Phi is a homomorphism. Since phi of, let us take two elements here, say sum gp plus sum of say hp. So this is same as phi of sum of say gp plus hp, which is same as sum of fp of gp plus hp. Now fp is an isomorphism, so this is same as sum fp of gp plus fp of hp. So which is same as phi of this sum gp plus phi of this sum hp. So phi is a homomorphism. One can easily define another homomorphism from gp to gp prime which is inverse of this phi. So phi is invertible because fp is an isomorphism, fp is bijective. So one can define here another homomorphism, say phi inverse from direct sum of gp's to direct sum of, so this is g prime p. So what it does, it takes an element here, So P inverse, it takes an element here which is say GP, so let us GP prime here. It takes this element to sum of FP inverse, because FP inverse is isomorphism, so it is invertible as well, so it is GP prime here. Now phi being invertible, so this phi is isomorphism, hence this group G, this is isomorphic to G prime. Now let us define the p-groups. So this is the definition here. So this is the definition of p-groups. So let us consider an element, let us consider a prime number p, and let G be an abelian group. So this G is a p primary abelian group. Let us consider a subgroup P of G. So P is a subgroup of G, it is given. Now we call P a pure subgroup if this intersection P intersection P and G, so if this is P and P, note that this is a subgroup of G, this is a subgroup of P. So if this intersection is this subgroup here, then P is said to be pure. So let us define this. Let P be a prime number. So this is given to be a prime number, and say let this G be a p primary abelian group. A subgroup P of G, a subgroup P of G is called pure if for all n bigger or equal to 0, this intersection P intersection P and G, this is P and P. So if this is the case, then this P is said to be pure. Now one can see here that this one of the inclusion is trivial, that is this inclusion is trivial. P and P, this is always contained in P intersection P and G, so this is trivial, one can see over here. So if we take an element here, so let X be an element of P and P. So if this is the case, now P and P, this being a subgroup of P and G, which is contained in P and G, so this X is in P and G. Also this X, this is so this, if this X is in P and G, so this X is of the form P n times Q, where this Q is in P, because X being an element of this P and G, so X has a form P and Q, where this Q is in P, that is this X is same as Q plus so on plus Q, this is P n times. Now each Q, this is in P, so this sum is in P, because P is a group, so this is in P. Now this X is in P and G, and this X is in P, so this X is in the intersection, that is this X is in the intersection P and G. So this is in the intersection, so this is in both P as well as in P and G. So we took this element in P and P, and we showed that this X is in this intersection. So this means this P and G, this is container in this set, that is this P and P, because we took an element here. We showed that this element also sits here. So this means this P and P, this is container in P intersection P and G. So it means to define a P group, only this inclusion here, this is significant. So let us make this remark. So one can observe that the inclusion, so this inclusion P and P, this is container in P intersection P and G, is always true. Hence it is the reverse inclusion which is significant. Yes, it is the reverse inclusion which is significant. Now this reverse inclusion here is, so it is the reverse inclusion which is given to be, and this inclusion P intersection P and G, container in P and P. So this inclusion is significant. Now what this definition says, it says that a group is a pure so let us make another remark here. So this is remark first. From above we conclude that if say if X is in this P, if this satisfies an equation, if this satisfies an equation which is X is equal to this P to the power n times say A for some A in G, then there exists say A prime in P with let us denote this element here by X prime. So then there X and X prime in P with X equal to P to the power n S prime. So P is a pure subgroup if each of its element, so if P is pure subgroup, then uh, each of its element has the form P and A, what is A is in G. So if this element has also this representation P power n S prime, where this S prime is in P, sorry, it is X prime here, so this is X prime here. So if each element of P, now if this X is in P